The wind power plant training system of Lucas Nulle is the best in its market, and today I'm going to show you why. But before we go to the system, let's get some facts and knowledge about wind power plants. Wind power plants account for one of the largest renewable electricity generation resources in Europe and many other regions in the world. Besides the visible outer components of the wind power plants, the most important components are located inside the machine housing. Some of these elements are the drive shaft, generator, gearbox, transformer, as well as braking mechanism. In principle, the wind turbine converts the mechanical energy from the wind into electrical energy. This is possible due to the state-of-the-art aerodynamic characteristics of the blades and other performance-enhancing equipment. Even though each wind power plant is designed and optimized according to the conditions of its installation site, they will all fit into one of the three main concepts. The first one is the constant speed direct grid-coupled type, or the so-called Danish concept. And the other two are the variable speed, full-fed, and double-fed generators. Here we are going to focus on the double-fed induction generators, which are widely used in the wind power plants. In this concept, we can utilize wind energy in an efficient way by means of the variable speed generator and the frequency converter. The wide range of control strategies in the variable speed systems has allowed them to establish themselves in modern wind turbines. The special advantage of this concept is the ability to control the active and reactive power for grid stabilization. You could observe so far that all this theoretical background can be found in our LabSoft courses. Besides, we have also implemented real-time evaluation and experiments to improve the hands-on skills. Our teachware includes a combination of hardware and software which are interconnected, meaning that all these hardware can be controlled via the virtual instruments included in the courses, and the measurements can be visualized and recorded. Let's have a look at the hardware now. Using this system, we are able to emulate the behavior of a real wind power plant in the lab. The wind power plant's most important component is the double-fed induction generator, or DFIG, and the servo machine test bench. Together with the control units, the aerodynamic and physical characteristics of a wind power plant can be emulated. The servo motor and the associated software is used to replicate the wind's behavior. For connecting to the grid, we use the three-phase power supply and this isolating transformer. The system can be used as a standalone, or using this intelligent measurement device, it can be coupled to the smart grid as one of its distributed energy resources. First, let's take a look at the operation of a double-fed induction generator. The stator of this generator is directly connected to the grid, and the rotor side is connected through the frequency converter. The fluctuation of wind conditions, the aerodynamic position of the blades, and other factors influence the rotor's speed of the generator. But the generator must produce the voltage at a constant frequency and amplitude to be fed to the grid. For this, the rotor's field will rotate in a way to compensate the variations. As the first experiment, I would like to show you the manual synchronization process of the wind power plant to the grid. I'm going to start the servo machine test system and give a speed of around 1200 RPM. This replicates the wind speed. Now I'm going to open the instrument synchronizer in LabSoft. You can already see the three-phase of the grid that is represented here. We know that for synchronizing to the grid, there are conditions that have to be met. These conditions are the frequency, the voltage, the phase angle, and the sequence of the grid and the generator that have to be the same. I'm going to enable the software and then increase the amplitude. You can see that these are real measurements, because if I, for example, remove one phase, you will directly see it. Now I'm going to increase the frequency to grid frequency. Then I have to increase the amplitude again. And now we will wait for the right time to synchronize. Of course, this operation can also be done in the real power plants automatically. Of course, the synchronization process can be performed in a real power plant automatically, but the purpose of a didactical system is that the students perform all the experiments on their own to get the best training. Like I have said before, the wind power plant can be used for reactive power compensation for grid stabilization. The reactive power can be drawn or fed into the grid depending on the situation. Now I will open the power control instrument and the phasor view to observe what is happening on the system. Here I will emulate the wind again. I will enable the instrument to establish connection with the hardware. By pressing Enable, the system will automatically synchronize to the grid. Once connected to the grid, the generator can either feed in or draw power from the grid. Arrows are used to indicate the flow of power within the various components. Increasing the excitation via the machine side converter beyond the rated excitation causes the generator to supply the grid with reactive power. The generation then acts like a capacitor. Reducing the excitation to below the rated level causes the generator to draw part of its required reactive power from the grid. You can copy all the diagrams from the virtual instruments to the LabSoft for further evaluation. The students can now evaluate their understanding by answering all the questions that are provided in the LabSoft courses. After performing many different experiments on the concept of the wind power plants and control strategies, we can move forward to a more advanced experiment using the Virtual Instrument Control Center. I will proceed to open the instrument. This instrument includes settings of wind speed, pitch control, wind profile emulation, and power control. Now I will adjust the proper settings, which are given in the course. And press Drive to connect with the hardware. We can either manually emulate the wind speed or upload the wind characteristics from weather data. I'm going to now manually increase the wind speed. When the speed is in the correct range, the generator synchronizes automatically and starts feeding power to the grid. I will now increase the speed even more. We can observe that the speed is now exceeding the limitations and the pitch control is activated through the optimal control of the blades and keeping the wind turbine on a safe range of operation. You can see that with this setup, you can perform many more interesting experiments and the students can acquire a very deep knowledge of this topic. Besides the wind power plants, we also offer training systems in many other topics such as photovoltaic systems, conventional power generation, smart grid distribution and cybersecurity, consumption and energy management, transmission and protection techniques, and many more topics. All combined can then form a greater system, namely smart grid.